Assalamualaikum warahmatullahi wabarakatuh. My name is Mama Aiman bin Hamad, and today I will present about introduction. First of all, emitter bias stabilized, a configuration in which a bipolar junction transistor or OBJT is reinforced with an emitter resistor for enhancing its stability with regards to changing ambient temperatures is called an emitter stabilized bias circuit for BJT. Other than that, voltage divider bias is the most popular and used way to bias a transistor. It uses a few resistors to make sure that voltage is divided and distributed into this transistor at correct levels. One resistor, the emitter resistor, also helps provide stability against variation in beta. That's why exists from transistor to transistor. The reason why we use voltage divider is because voltage divider bias will give better stability compared to all other circuit.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faizi bin Muhammad Fikri. Matric number AA212547. Now I want to present to you about design 1. For the beta and VCC, been given that beta is 45 and VCC is 70 volt. So from the data sheet, we get the IC set is equal to 500 milliamp and IC max is 0.6 ampere. So we can find the ICQ, which is ICQ equals to 1 over 2 IC set. So we can find it with 1 over 2 times with 500 milliamp. So we get the ICQ equal to 250 milliamp. So we know if ICQ, the IC equals to IE, which is 250 milliampere. So next, so from the table data sheet, we can find the VC, which is 0.5 times with VCC 17 volt, and we get the answer for VC is 8.5 volt. For VE, we can find with 0.15 times with 17 volt, and we get the answer. For IE we use the formula for find the IE. We use the formula IE equal to beta plus 1 times with IB. So we got the IE 250 milliamp equal to beta 55 plus 1 times with IB. So IB we get the 4.46 ampere. So next is we need to find the RC. RC we use the KVL formula, which is VCC minus ICRC minus VC equal to 0. So VCC 70 volt minus 200 milliampere times with RC and minus 8.5 volt equal to 0. And so we get the RC 34 ohm. So to find the RE, we use the Ohm's law. VE equal to IE times RE. So VE we got the 2.55 volt equal to 250 milliamp times with RE. So RE we got the 10.2 ohm. For VCE, use the VCE minus VC minus VE. So VC we got for this 8.5 volt minus 2.55 volt. So VCE we got 5.995 volt. So RB we use the formula KVL, which is VCC 17 volt minus IB 45 4.46 milliamp times with RB, so minus VBE we got 0.7 volt minus VE 2.51 volt, so equals to 0. So we got the RB, that is 3.08 kilo ohm. So that's the calculation we got. So next is for the simulation for design 1. So this is my circuit for design 2, and I will run. Actually the value for IBRP, IBIC, IBRC is totally different with the calculate before this. So the VB is 12.8 volts, and the IB we got from the simulation we got 4.15, and VC we got 11.1 volts. IC we got 327 milliamp. For the IE we got 331 milliamp, and for the VE we got 3.38 volts. So that's all for me. Thank you.
Assalamualaikum and salam sejahtera. My name is Muhammad Atisafi bin Syafrizal. Number matrix AA210840. So today I will explain about the calculation for simulation 2. So the first one that the question give us is VCC is equal to 17, beta is equal to 55, IC saturation is 500 milliampere, and IC max is 0.6 ampere. IC is 250 milliampere and ICQ is 250 milliampere. So as we know, how to if we want to get an IE, we have to make to plus IC plus IB, which IE is equal to 250 milliampere. So the way to get VC is 0.5 times with VCC, which 0.5 times 70, and we get 8.5 volt. So VE is 0.15 VCC, which is 0.5 times 17 is equal to 2.55 volt. So if you want to get IC, we have to use formula beta IB, which IB is equal to IC over beta, and 250 over 55, and we get 4.45 milliampere. If you want to get VCE, we have to use VC minus VE, which the value is 5.55 volt. So for the RE is equal to VE over IE, which 2.55 over by 250, and we get 10.2 ohm. So for RC is VC over IC, which 8.5 over 250, and we get 340 ohm. So for the R2, we have to use 0.1 BRE, which 0.1 times 55 times 10.2. So we get 56.1 ohm. So for the VB, we have to use VBE plus VE, which 0.7 plus 2.55, and we get 3.25 ohm. So for the VB, we have to use R2 over R1 plus R2 times VCC, which VB we got 3.25, and R2 is 56.1, and R1 plus 56.1 times 70. So we have to arrange it for one equation, and we get R1 is 771.37 over 3.25. So the R1 is 237.34. So for the R1 is R2 in bracket VCC minus VB over VB close bracket, and we get 56.1 open bracket 17 minus 2.55 over 3.25 close bracket, and we get the answer for R1 is 237.34. So for the IR1 is equal to IR2 plus IB equal and for the value is 757.93 plus 4.54. So the equal is 62.47 milliampere, and IR2 is equal to VB over R2 and 3.25 over 56.1, and the answer is 57.93 milliampere. So that's for the calculation for simulation 2. So I will show about my circuit today. So for the VR1 I got 15.5 and IR1 is 0.08. So for the VR2 I got 1.86, and for the IR2 I got 0.03. So for VR3 I got 16.1 watt, and for the IR3 I got 0.04. So for the VR4 I got 0.80, and for the IR4 I got 0.07. So I think that's all for my circuit. Thank you.
For the conclusion, first of all, amplifiers are particularly useful in converting a tiny signal such as voltage, current, or power into a bigger signal. Second, under signal circumstances, a small signal amplifier only utilities a small portion of its load line. Third, the voltage gain of a small signal amplifiers is calculated by dividing the output voltage by the input voltage. It is because it has the highest voltage gain. The common base small signal amplifier is the best for amplifying voltage. Fourth, the voltage gain of the common collector small signal amplifier is the lowest, and there is no phase mismatch between the input and output signals. And the last one is the base of a common base small signal amplifier is a common terminal to the analog signal, while the collector acts as the output. So that is all for our group, and thank you.